when this goes from here to here, then obviously there are going to be some losses, there are going to be some gains. But there is no dissipative forces like friction, etc. So the total mechanical energy of the system will remain conserved. So there are going to be some losses and there are going to be some gains, as we had done earlier in our chapter work, energy and power, and then we have said that is losses equal to gains if there are no dissipative forces. So we see that is, if we consider it has only two things, it is translational motion, so it has only two terms of energy. One is gravitational potential energy, the other is kinetic energy. Gravitational potential energy, we generally say it as potential energy only. So when the body goes from here to here, so obviously there is a loss. So loss is mgh, that is 10 into g is taking as 10 only, into h is 2. So this is loss of potential energy. What about kinetic energy? So when it goes from here to here, the velocity is u over here the velocity is v. So it means the velocity has increased, it means the kinetic energy has increased, it means gain is half into 10 into v square. Now coming to this disk or whatsoever it is, because it has not been given this is a disk, there could be a different kind of mass of distribution, so you cannot use directly I as mr square by 2 about this axis. They have directly given 15 kilogram meter square I is given. The center of mass of this disk, it is not moving anywhere, so potential energy, there is no change in potential energy of this. Is there any change in kinetic energy? Yes, there is change in rotational kinetic energy, though translation kinetic energy doesn't change, but it has started moving, and we know that is the rotational kinetic energy associated with the body of I moving, having angular velocity omega is half I omega square. So initially when it was not rotating, the rotational kinetic energy of it was 0, but now if it is rotating with omega, then it has kinetic energy has increased, that is rotational kinetic energy has increased, that is half I omega square. I is, that is half I omega square is, you know, that is rotational kinetic energy. Analogous to translational kinetic energy, when we say translational kinetic energy, it is half mv square, and in rotational, the analogous of m is I, of v is omega, so half I omega square is rotational kinetic energy. So half I omega square. So it means, but over here we have v also, we have omega also. Is there any relationship between v and omega? Yes, the same kind, that is what we have done for acceleration, we can use for v also. The linear velocity of this is v, linear velocity of this is also v, linear velocity of this is also v, linear of this point which is at the periphery, that is also v, and this is at this moment it is also moving in a circle also. So we can use v is equal to r omega, that is v is equal to r is 1, v is equal to 1 omega. So this is a relationship which connects the translation motion and rotational motion. So over here we can use v is equal to r omega, so omega is equal to v by 1. Now we say loss is equal to gains, so losses 10 into 10 into 2 is equal to half into 10 into v square plus half into 15 into omega. Omega is v by 1, so it comes out to v square. So this comes out to be 200 is equal to half into 10 plus 15, 25 v square. So this comes out to be 400 by 25 is equal to v square, and v comes out to be 4 meter per second. We get the same answer as we have found by the dynamic principle, that is where we have taken the forces into consideration, forces and torques. That is a vector method over here. This is scalar method, energy methods, they are the scalar methods. We have got the answer, same answer as we have got it by this dynamic method.